For today, we will be discussing the settling and sedimentation. In settling and sedimentation, the particles are separated from the fluid by forces acting on the particles. You can find the formulas and discussion pertaining to sedimentation at section 6 and 18 of your Paris Handbook, both for the 7th and the 8th edition. Some of the common application for settling and sedimentation, we have the removal of solids from liquid sewage wastes, settling of crystals from mother liquor, separation of liquid-liquid mixture from a solvent extraction stage in a settler, and the settling of solid food particles from a liquid food. By definition, sedimentation is the tendency for particles to settle out of the fluid in which they are entrained and come to rest against a barrier. Sometimes sedimentation is done through gravity settling, and it is also the separation of dilute slurry or the solid suspended in fluid into a clear fluid and then slurry, which is the higher solid content by gravity settling. In the sedimentation process, it typically involves a certain particle and of course a fluid. Some of the factors affecting the sedimentation process is we have the particle size, the liquid viscosity, and the solid and solution density. And we have the types of particles, which are the totally discrete particles and the flocculent particles. We also have the different types of sedimentation, which are the free settling and the hindered settling that we are going to talk about later on this lecture. For the sphericity, it is defined as the ratio of the surface area of a sphere having the same volume as the particle to the surface area of the particle. So as you see on the illustration, it is the measure of how closely the shape of an object resembles a perfect sphere. In finding the sphericity of a particle, we have these formulas that we can use in order to find the sphericity of certain object. Take note that in using the sphericity or in finding the sphericity, the volume of our sphere is equal to the volume of your particle. And for spherical particles, the sphericity is equivalent to 1. And for non-spherical particle, we will be using the formula 6 over dp, or the particle diameter, divided by the surface area over the particle volume. Take note that in non-spherical particle, the particle diameter should be the equivalent diameter in terms of sphere. So the dp there should be, since hindi nga siya spherical, we need to get the equivalent diameter of that particle. We are asked to find the sphericity of a cube having an edge A. So let's take our cube, the illustration of our cube. And having a diameter, edge of a variable A. So the formula for finding the sphere, we have the 6 over the particle diameter divided by the surface area of our particle divided by its volume. So if we are not talking about a spherical particle, we need to get the equivalent diameter of our particle using the diameter of our sphere. So let's take let's have the diameter of our sphere as DSP, and in getting the volume of our sphere using DSP as its diameter, we have the volume of our sphere pi DSP cube divided by 6. So take note that by definition, the volume of our sphere is equal to the volume of our particle. So let's get the volume of our cube, since the cube is our particle at this example. Using the edge A, in finding the volume of our cube, the volume of our cube is a cube. So let's have, to get the equivalent diameter, let's equate the volume of our sphere to the volume of our particle. So simplifying the equation to get the DSP, so this is the DSP. So this term is the one that we will substitute for the DP of this equation, for the equation of our sphericity. Now we need to get the surface area and the volume of our particle also. For the surface area of a cube is simply 6a squared, and the volume of the particle is a cube. Now, in finding the sphericity of the cube, we will now use the formula of 6 over dp divided by the surface area over the volume of our particle. 6 dp, we will use the DSP, since it is the equivalent, the value of DSP is the equivalent diameter. So our DSP is 6 over pi raised to 1/3 times a divided by the surface area 6a squared over a cube. So simplifying this equation, we will arrive to the value of we will arrive to a value of 0.806. So the sphericity of a cube having an edge A is equal to 0.806. So that's how you find the sphericity of non-spherical particles.
Now, for the types of sedimentation, we have the free settling and the hindered settling. In free settling, the particle has a sufficient distance from the other particles so that the fall is not affected by them. While the hindered settling, it occurs when the particles are crowded so that they settle at a much lower rate. So in particle motion, the external force is expressed as a product of the mass and the acceleration of a particular particle from this force. So this is simply the Newton's law. This equation, if F is equals to mass times acceleration, is pertaining to the Newton's law.
The mechanism of the particle motion through a fluid. The three forces acting on the body is the external force acting downward, the buoyant force, and the drag force in opposite direction. The external forces and the gravity of the body are opposed by the buoyant forces and the drag force. Following the Newton's law, the summation of force is equal to the mass times acceleration. And the forces is the external force, the buoyant force, and the resistance or the drag force in opposite direction to the particle motion. If the motion is from gravitational force, the acceleration is equal to the gravity. And if it is from the centrifugal field, the acceleration is equal to Rw squared. Since one of the forces acting on the body is the buoyant force, the buoyant force based from Archimedes' law, this is the product of the mass of the fluid displaced by a certain particle and the acceleration from the external forces. So, given in your screen is the formula for the buoyant force. For the formula of drag force, flash in your screen, CD is the drag coefficient and AP is the projected area of the particle in the plane perpendicular to the flow of direction. So you don't need to memorize this formula. You can find this formula in your handbook, Paris Chemical Engineer's Handbook. So substituting and rearranging all the formulas that we have discussed, we will arrive to this equation number 1. So you can use this if we are talking about the mechanism of particle in motion. The falling of the body consists of two periods. We have the period of accelerated fall and the period of constant velocity fall. In the period of constant velocity fall, there lies the terminal settling velocity or the free settling velocity that we can get in using this equation. So all of this equation are also can be found also in your Paris Chemical Engineer's Handbook. So you don't need to memorize all these formulas written or flash in your screen. So for a free settling velocity, you have to use this formula. So the free settling, there is no hindrances to the motion of the particles that we are talking about. Now, we have different formulas to be used when we are talking about the terminal velocity for a free settling period. So we have to determine the range in which our motion lies. So we have different region. We have the Stokes law region, the intermediate law, and the Newton's law. So we need to identify first the value of our K or the value of our Reynolds number in order for us to know if what formula we will be using in solving for the terminal velocity of a free settling period. Now, if we already have the value of k, we can now determine the formula or the region that we will be using in solving for our terminal velocity. If it is for the Stokes law region, intermediate law, or the Newton's law. So, depende sa value ng k natin kung ano yung gagamitin yung formula to get your terminal velocity. If ang ginamit nating determination ng range in which our motion lies is the k, pwede rin. And also, if wala tayong k and wala tayong way para makuha si k, we can also base our motion range sa Reynolds number. We can also determine the value of k if we are talking about the terminal velocity for a hindered settling. So, ito naman yung formula ni k if we are going to solve a hindered settling type of problem. And then, in a hindered settling, we have the so-called empirical correction factor. Ito ang kanyang formula flashed in your screen. And then the epsilon like there is what we call the that is the voids of the particles or the void volume. So this is the formulas to be used if we already determine the k values for a hindered settling. Ito naman yung mga formulas to be used for getting the terminal velocity in a hindered settling period. And also, hindi lang k ang pwede natin gamitin, yung equation ng k for the free settling period, yung na-discuss ko kanina. Yung k, if wala talagang means na makuha si k or si Reynolds number, you can use the Archimedes number. It can also be found in your Perry sa section 6. So, yung Archimedes number, it will also help you to determine in which the motion range lies. So, meron naman sa Paris na guide. So, kindly read na lang sa Paris kung paano ginagamit yung Archimedes number. Nandun din naman yung mga legend ng formula. So, for getting the terminal velocity of hindered settling, this is the formula. And this is the legend of those symbols. So, as you can see on your screen, we have the graph for the Reynolds number versus the drag coefficient. So this graph is very useful if, example, meron tayong given na drag coefficient. You can already predict or you can already know the value of the Reynolds number by simply using this graph. Kasi project nyo lang so kung anong type ng particle, then project nyo kung saan kayo kukuha ng Reynolds number. So, for example, meron tayong drag coefficient. From left, ipoproject nyo siya papunta kay sphere, kung sphere yung particle. And then, kapag natamaan nyo yung curve ni sphere, project nyo siya pababa. Then, makukuha natin yung values ng Reynolds number for that particular particle. For the problem, we need to determine the terminal settling velocity of dust particles having this given. So, we need to find the velocity. So, this will be our unknown. And the given in the problem is we have the diameter of our particle, which is 60 microns. We also have the temperature, (294.3 Kelvin), and we also have the pressure, 101.32 kilopascal. Also, the density of our particle is also given.
value is 1,280 kilogram per meter cube. Now, the parameters that we need to get is the viscosity and the density of our fluid where our particles is moving. So these two can be determined using interpolation in the data that is located or that you can find in your Paris. So I presume that as of now you know how to interpolate data from Paris. So the fluid that we are using or the fluid that we need the details is fluid of the air fluid, since this is a dust particle. So the data you will be getting your data from the air that you can find in your Paris. So I already looked, or I already interpolated the value. So I got 0.01821 times 10 to the negative 3 Pascal seconds. So this is for the viscosity of the air, and the density that I got is 1.234 kilogram per meter cube. So kindly check it out if we have the same values for these parameters for the fluid air. Now, in order to get our settling velocity, it is also, our unknown is also denoted sometimes as UT, meaning this is that velocity. So we need to get the value of our K to know which formula we will be used to get the value of our velocity. So K, or the Archimedes number, whichever you prefer. The Archimedes number can be found, for the formula for the Archimedes number can be found also on your Perry. I think this is chapter 6 -236. This is the equation for the Archimedes number. So you can also use this to determine which formula for terminal settling velocity you will use. So for the K, we need to determine the value of K, so we will know the formula if it will fall to the Stokes law region, intermediate law, or the Newton's law formula. So let's get the value for K. The K has a formula that is given in our lecture. So I discussed it. So this is the particle diameter times the gravity, the density of the fluid times the particle diameter minus the density of our fluid, then divide it into our viscosity raised to 1/3. So let's substitute the necessary parameters or the values to find the value of our K. Make sure all your units are in SI, since we are using SI units here. So we will now input the values. This is squared. So the value of our K is 2.1589. So since our K is less than 3.3, the formula that we'll be using falls to the Stokes law region. So the formula for Stokes law is the one that we will be using to compute our terminal settling velocity. So for the terminal settling velocity in Stokes law, we will use we are going to use this formula as stated in your or as given in your lecture. So substitute the necessary values calculating the values in our equation. We've got the value for our settling velocity 0.1378 meter per second. So this is the value for our terminal settling velocity. So that's it. That's how you solve problems regarding terminal settling velocity. So the problem is a hinder settling type of problems. What the difference of the hinder settling from free settling? The hindered settling, it usually occurred when the particles are crowded so that they settle at a lower rate, while the free settling, the particles has sufficient distance from the other particles so that the fall will not be affected. So in this problem, we will be talking about the hinder settling. So we have we need to determine the hindered settling velocity in this problem. we have given, based from the problem, we have the particle of the diameter 0.09 millimeter. Let's make it in meters. Then we have the density of our particle. And also the temperature, 26.7 degrees Celsius, also equivalent to 299.85 Kelvin. So the fluid that we are talking about in this problem is water. So we need to know the parameters, or the parameters needed for our formula for our fluid water. So we need to get the density and the viscosity of water based from its temperature. So where we can get the values for the density and the viscosity of water from our handbook, Paris Chemical Engineer's Handbook. So I already got the values using interpolation in our steam table, since we are dealing with water. So the values that I got for density 9965490, and the viscosity so since this is a hindered settling, the velocity for a hindered settling can be computed by the equation discussed in the lecture. So let's check if we have the following parameters needed in our equation for hinder settling velocity. So the gravity, the particle diameter, the density of our particle, the density of our fluid. We have the void, so we don't have the value for the void yet. And then we have this empirical correction factor divided by 18 times the viscosity. So before putting all the values, let's get first the value of the voids. So what is that void? So ano ba yung tinatawag na void? If we have this container, so puno siya ng solids, so the void that we are getting is the spaces that doesn't consumed by our solid. Yung mga spaces dito, that is what we call the void. So we will be getting the value of the void since the volume fraction of our solid is given. We can get the value of the void simply by 1 minus 0.45. This is the volume fraction of our solid. So we have the value of void as 0.55. Next, we have also the empirical correction factor. So as stated in the lecture, we have the formula in getting the empirical correction factor. 1 over Let's compute. So the empirical correction factor has a value of 0.1517. So let's input all these parameters or all these values in our formula. Make sure you have a uniform unit. If SI, use all SI. Convert all your unit into SI. If English, convert all your unit into English. So the hindered settling velocity that we are looking is 2.3767 times 10 to the negative 4 meter per second. So this is how you solve for a hindered settling type problem.
For a certain batch sedimentation, this is a unit operation used to separate an initially dilute slurry to a clear liquid and a final slurry of higher concentration by, of course, the gravity settling. Now, we have this batch sedimentation test. So, in this illustration, you can see that it is a batch sedimentation test. So, initially, to the first cylinder, we have the zone B only. So, ito yung initial stage ng naglagay tayo ng particles to our fluid o yung initial na pag-join ng particle and fluid. So, sa zone B, this is the slurry which has some property as the initial slurry. So, initial stage to. For the second cylinder, we now have the zone A, zone B, and zone C, and zone D. Ito na, nag-start na siyang mag-move yung particles natin. Nag-start na siyang mag-settle at the bottom of our cylinder. Pero slightly settling pa lang itong second cylinder. On the third cylinder, you can see the movement of the particles. Nagiging mataas na yung layer ng zone D natin, which is the compacted solid, or dito na yung nagsasettled na yung particles. For the zone Z, this is the higher solid concentration. Mas madami dito nag-start para magpunta doon sa pagsasettle niya sa zone D. And for the B, ito yung scenario for our initial slurry. And for the zone A, this is the clear liquid zone. So, umaalis na sa kanya yung particles na meron. So, fluid na lang yung natitira kay zone A. For the fourth cylinder, so, nakikita na natin yung changes. Lumalaki na yung layer ng zone A natin at the same time yung zone D natin. Lumiliit naman yung zone B and zone Z kasi nagsasettle ng fluid, nagsettle na yung particles, nag-start ng maghiwalay ang particles and the fluid. And then for the fifth cylinder, dito na yung may critical point kasi nagsisettle na yung mga particles at the bottom layer of the fluid, and then nag-start na din lumaki yung clear liquid zone natin, in which dun sa clear liquid zone, bumababa na yung particle at the bottom. So meron na tayong, at the sixth cylinder, we have an established sedimentation, or nagsettled na completely yung particles natin at the bottom of the fluid. So for the formulas that we are going to use in this batch sedimentation, for a free settling, meron tayo dyan yung time of the commercial tank divided by the original height in that tank is equivalent to the time if we have the batch test divided by the original height in our cylinder during the batch test. We also have the rate is equal to the original height minus the height of the sludge at the end of the free settling period divided by the time. This is for the free settling, and for the hindered settling, we will be using the ln ZO minus Z infinity. Infinity is the time or the height of the sludge when it settled completely, divided by ZC, the height of the sludge at the end of the free settling period, minus the Z infinity equivalent to K is constant, times the quantity time minus the time in which it settled, or at certain time if merong given sa problem na hinihingi at during that time, that particular time. Sedimentation, batch sedimentation problem. So let's illustrate the given problem. Originally, the height of our sludge before settling, we have 10 inches. And then it goes down to 6.5 inches. And then the height of our sludge at the end of 120 minutes is 4 inches. So this is 120 minutes. And the height of the sludge settled completely is 1.5 inches. So we need to know the time for the commercial tank. Let's have the illustration for our commercial tank. So using the same sludge, the volume of our tank is 1,000 cubic feet. And then the diameter of our tank is also equivalent to the height, to the depth of the liquid suspension. So
let's say so 1 is equal also to our diameter. And then we will be determining the time it would take for the solid to settle to a height of 20% of the original sludge. So, the time in which 20% original sludge so let's take first the necessary equation that we will be using for batch tests. In free settling conditions, so this is the height of our solids before settling, and this is the height at the end of the free settling period. And then this is the rate. Another equation is the commercial tank equivalent to the batch tank. This is the time of the commercial tank divided by the original height, and of the commercial tank, and then this is the time for the batch test divided by its original height. So another equations that we will be using is for the hindered settling. For the hindered settling, we have Ln so this is our height of our solids before settling minus the height of the sludge settled completely divided by the height of the sludge at the end of the free settling period minus the height of the sludge when settled completely. And this is the time now. Let's start solving our problem. So first, let's take the free settling or the batch test formula. So when the original height is 10 inches and before free settling our height is 6.5 inches, so this is the point before the free settling. The one that settled completely is this illustration, and our rate is 0.1 per minute. So getting the time, we will be using this formula kasi nasa free settling period pa tayo. So 10 minus 6.5 divided by 0.1. The time at the end of the free settling period is 35 minutes. Now, let's go on to the hindered settling. So, start tayo kay hindered settling at the end of 120 minutes. So, we will now be using this equation. This is for the batch test. The hindered settling. Take note, this is for the free settling conditions. Free settling period happening on our suspension or on our sludge. So let's move on to the hindered settling period of our sludge in our batch tests. When we have the height of our sludge in 4 inches at 120 minutes, we're solving for this is our original height at the end of 120 minutes. 4 minus the height at which our suspension settled completely is 1.5, and then end of the free settling period is 6.5 minus 1.5, negative k. K is unknown. This is supposedly constant. Then 120 minus 35. So we will now have the value of k. Eight 8.51547 times 10 to the negative 3. So this is the hindered settling period of our sludge. Let's go on. Since the sludge used in our batch test and in the commercial tank is the same, we can use the data in that commercial tank for the hindered settling period. So when we have Z is equal to, since sabi sa problem 20% of the original height, so let's take 20%. Our original height in our batch test is 10 inches times 10. So we will be using Z, assuming sludge settled completely 2 inches. So let's input the values using the hindered settling formula. ZO now will be 2 minus 1.5. 6.5 minus 1.5 equals to negative 8.1547 times 10 to the negative 3. And then our time now, time is unknown kasi hindi natin alam kung anong time nagsettle completely si 2 inches natin. So, unknown, siyang magiging unknown, then minus 35. So, calculating our time, we now have 317.3629 minutes. So, sa 317.3629 minutes, nagsettled ang ating sludge in 2 inches. Kung itong 2 inches ay nakalagay sa ating batch test. So, this is also equivalent to the time for the batch test. So, in determining the time in commercial tank, dun sa actual commercial tank niya, we will use the equation, this one, kasi may correlation si batch tank into the commercial tank. The unknown should be the time for the commercial tank for the 20% of the original height to settle completely. Now, the height, the original height dito sa tank is unknown. So, hindi natin alam din kung saan height siya nag-start bago siya settled papunta sa 20% of the original height. So, we need to know first the height of the depth of the liquid in this tank. Paano yun? I-correlate natin siya sa kanyang volume. So, volume of tank, the volume is pi d squared over 4 times the height. So, since ang sabi sa problem, the diameter is also equivalent to the height, we can just simply make this pi d cube over 4. So, the volume, we have the volume 1,000 cubic feet pi d cube over 4, having a diameter of value of 10.8385 feet. So, converting this feet into inches, 0.9032 inches. Now, this will also be the value of our height since they're equivalent as stated in the problem. So, we can now move to our equation here. Para malaman natin yung time na nagsettle si 20% ng original height, so we will now use this equation. So, yung height natin na nakuha, 0.9032 times the time dun sa batch tank, 317.3629 minutes. So, let's make it in hours. Convert natin sa hours. Then, the original height dito sa batch test natin is 10 inches. Inches to. So, gawin lang natin doon in hours. So, 60 minutes, 1 hour. No, correction. For this one, this is 10.8385 times 12. So, this is 130.062 inches. So, this is this is 68.7948 hours. So, this is the time that it will take
20% of the original height times. Para ang maging height niya dito is 26.0124 inches, it will take 68.7948 hours for it to settle in that height.